Greetings, I'm Marijke Jorritsma here with Adrien Maillard to go over a scheduling language and companion UI that we've developed for the Europa Clipper mission planners to achieve their desired scheduling outcome. This work is funded by Europa Clipper and AMOS, a NASA program aimed at providing generic ground system hardware and software for missions. AMOS's objective is to develop the next generation of multi-mission scheduler. Europa Clipper's operational concept relies on the use of an automated scheduler and is thus able to provide realistic use cases for the development of this work. Europa Clipper is a NASA interplanetary mission. One orbiter will perform 44 close flybys of Jupiter's moon of Europa. On board, there are 9 instruments that will study its ocean, geology, chemistry, and habitability. We've conducted numerous user sessions with Europa Clipper mission and science planners to collect feedback on the scheduling grammar and use cases.
Let's now see the main scheduling concepts that we can represent and how these concepts translate to a grammar implemented in Java. First, let's look at the Europa Clipper example to see what kind of construct we need. A different one present in the paper, the scheduling of data downlinks via the deep space network. So scheduling goals can specify what activity users want to schedule, when, and sometimes how to schedule it. In this case, the objective is to schedule 3 types of activities: downlinks during passes, and then pre-pass and post-pass activities before and after each pass. A downlink pass can be modeled as a conjunction of 9 state constraints. Then, for pre-pass and post-pass activities, it is quite straightforward. We must have one before each pass and one after each pass. Then for downlinks, we must have one activity per downlink rate as it changes over the pass. And each activity has a variable lookup time, which impacts its duration. Another constraint is that we should not turn off the transmitter between passes if those are sufficiently close to each other. There is a constraint on one of the parameters of the downlink. Usually, any data can be downloaded, science or engineering. But if at any point during the downlink there is a concurrency with a certain type of activity, we should switch to downlink of engineering data only. For Clipper, we must be able to model more than 200 cases like these. There are several types of goals. There might exist several variations for each of these categories. A frequency goal can be, there exists a same instance of activity type A every 10 seconds. A cardinality goal is less restrictive and only specifies that there must be a certain number of instances or total duration of the same activity type within a time range. A coexistence goal allows to specify that we should insert an activity whenever something else exists already, whether it is a state value, a conjunction of state values, or another activity. There is also a need to be able to integrate external activities resulting from the run of an external scheduler, such as an instruments scheduler. In that case, the goal will try to insert the activities and check other scheduling constraints to see if the computed plan is compatible with other activities. Now we'll briefly go through the main kinds of constraints that we have in our grammar. First, we need to represent desired conditions over states. States here are represented by variable time index values, timelines. Conditions can represent periods of time during which we can or cannot schedule activities, or during which we want to schedule an activity. Here on the picture, we can see a conjunction of 3 conditions representing what could be defined as a simplified download path for Clipper. The first state representing the availability of the DSN must be active, the occultation must be false, and so on. In this expression, if this expression was queried over a certain time horizon, it would return the set of windows during which this conjunction is equal to true. Realistic constraints are large conjunctions or disjunctions of state constraints. Going on with these expressions, the user sometimes has the need to take the expressions and to modify them or build other expressions from them. We have a certain number of filters and transformers that can modify the windows returned by these expressions. On this example here, we take the previous pass windows expression and we apply first a filter on them that filter out windows that are too small in duration. Then we apply a transform operator that contracts each window by a certain margin duration that may be used to model a delay before an activity can start. This makes this grammar in between a declarative grammar that would only describe the goal and an imperative grammar that would describe how to achieve it. Then we have the ability to express different types of goals. For that, it is necessary to combine activity types, state constraints, and relative timing. Here we have a simple example of coexistence goal that schedules one post-pass activity for each period satisfying the constraint in blue. And you can see that we can specify a relative start time for each activity corresponding to the end of the coexisting period. So activity start times may be defined relatively, but it can be more complex than that and be context dependent and dynamic. In this example, the start time is defined with a delay with regard to relative anchor, and this delay is sequence dependent. In each pass window, the first delay will be more important than the following ones because locking up the signal takes some time. And we also have composite goals, such as the one here made of a conjunction of sub-goals that represent the scheduling of activities for one of the instruments on Europa Clipper. One sub-goal exists for each kind of activity, and they are all aggregated together.
To extend access of the scheduling software to users who are not familiar with programming in Java, we designed a companion UI to provide users visual guardrails for authoring expressions and goals that achieve their intended scheduling outcome. Our design proposes that the UI and code editor be situated side by side so that the user can see how the UI translates into code and vice versa. We imagined that the UI would be a series of blocks that users could find organized in a toolbox in their application. In this demo, I will show you what it would look like for a user to construct a scheduling goal that includes a geometric constraint and a coexistence goal. The code that the UI would be creating is displayed in the box to the right. The first block that we see here is a goal block. The user can rename it to renames it to roll goal after the instrument calibration that they'd like to schedule. Next, they add a definition block. And in the definition block, they have a selector that specifies that for each activity type known as a PIMS role, something will happen. In this case, we are assuming that a PIMS role activity has already been defined outside of this flow. Inside the definition block, we add a geometric constraint block. And here the user can go through and specify the values for each of the parameters that they have drop-downs for in this box. So here the user has specified that when Jupiter has a distance that's less than a 15 radii of Jupiter, there exists something. And here they can specify the frequency for which they want that to exist. They specify 1 and they add an activity to the box. They can choose from a drop-down the activity that they would like to schedule, and then they can connect parameters that relate to that activity. So here our user specifies 4 different pointing vectors that would be related to that slew.
When the users has expressed all of the goals, they are passed to the scheduler. Each goal is associated with a priority, and then the scheduler is a greedy priority-based scheduler that processes one goal at a time in a decreasing order of scheduling priority. And for details about this, you can go and see the paper. Now let's look at related work and future work. So there is considerable academic work towards defining planning languages with PDDL, NDDL, or NML, for example. The expressive power of NDDL or NML in our cases probably makes them able to express scheduling goals, but they do not have the high-level operators and goals that we need, the scheduling goals. These languages are geared towards planning when we are focusing on scheduling. And as users are not planning and scheduling experts, we do not expect them to change their mindset from scheduling to planning to be able to use these languages. So work closer to our needs at JPL are APGen, which is the product we are destined to replace. It uses a purely imperative language in which every goal can be described as an algorithm and actually inserts activities. There is also the adaptation of Aspen for the Rosetta mission, a return of experience we use to define requirements for this work. There are many areas for future work, but we detail only 3 related to the language and UI. One is to allow users to express preferences or soft constraints. Another area is planning. The goal is to go from scheduling to planning for a number of things, such as attitude or pointing, where a more centralized approach could allow to schedule more activities overall. For the UI, we need to produce a syntax editor that works in real time with the UI and continue developing design patterns based on user feedback and emergent use cases. Thank you for listening. We are happy to answer questions, hear your comments and ideas.